Good morning, everyone. So this morning I'm going to talk to you more about the actual chemistry that is occurring in the small bodies of the solar system and from where it might be inherited from. On Monday, I told you about the tools. Yesterday, I told you about observations. And now I'm going to try to help you to understand why we find that. Because if you remember, we had that discussion about panspermia on Monday. And panspermia is a fact somehow to say, okay, we don't understand why life appeared on Earth. Okay, let's say it came from somewhere else. And you don't understand how it appeared somewhere else. But you think you brought some kind of answer to the question of the origin of life. You could say, okay, these chemists, they are doing the same. They are saying, okay, life might be promoted by the importation of organic molecules that were brought by meteorites, comets during impacts, and that's initiated the chemistry. And it doesn't tell you necessarily how those molecules formed, but it's not true. We know, actually, we are able to track the history of those molecules, and they can teach us a lot, not only necessarily about the origin of life, but about the origin of our solar system. Because when you are able to read the book of organic chemistry, not only to be scared by a list of complex molecules and to be impressed by hundreds, thousands, millions of molecules, but when you start to be able to decipher this origin, the mechanistics that is behind that, you can learn a lot. So what do we call small bodies? Small bodies basically are asteroids and comets. And there is no such thing as two boxes where you put asteroids and comets. You have probably some asteroids that are extinct comets. In the asteroid belt, you have what we call the active asteroids. So there is a link between those two families. And you have some subgroups like Trojan, Centaurs, extinct comet, asteroids, the Kuiper belt, and Oort close object. I would not get too much into the details about that. And a way to study these objects are to go there. Then you go to an asteroid, you go to a comet, or to collect on Earth samples, or to bring back samples to Earth. But you naturally have some samples that are brought to Earth from these objects. These are meteorites and micrometeorites. So it's sure, and I will bring you some proof about that some meteorites come from asteroids. Whether or not some meteorites or micrometeorites are coming from comets is still debated. We don't know. Probably some micrometeorites. Regarding meteorites, I think there's no evidence that any of the meteorites we have on Earth come from any comet. But it's still open to discussion. On this slide, you see a timeline of two extremely important space missions that are ongoing or just finished. This is a timeline of the Hayabusa 2 mission, a Japanese mission that went to an asteroid, collected sample at the asteroid and brought it back to Earth. And it was returned in December 2020. So the first results have been published, and in the coming weeks much more will be released by the scientific team of this of this mission. And then NASA launched a few years after another mission to another asteroid. It's called OSIRIS-REx, and OSIRIS-REx is now on its way back to Earth to bring the samples back. Japanese already brought samples back to Earth. It was Hayabusa 1 mission, but the target of the mission was more like a rocky asteroid dominated by rock. So it was a success. It brought only a very, very small fraction of material. We thought first nothing was brought back, but they found some sample from the asteroid. But those two missions aimed for carbonaceous asteroids. So carbonaceous asteroids are what we think the parent bodies of carbonaceous chondrite. But when you find a meteorite on the floor, well, you don't know where it comes from. You don't know if it's really representative of what you observe from with remote sensing technique from the Earth. So the advantage is that you know where you go and from where you collect your sample. And then you can try to relate that to samples you have in the laboratory. You don't go to the asteroid belt. The asteroid belt is too far away. Here you see the orbit of the Earth, the Sun, and the orbit of the two asteroids that were the targets of the mission. So Ryugu and Bennu. Ryugu was the target of OSIRIS-REx 2, Bennu the target of Hayabusa 2, and Bennu the target of OSIRIS-REx. You can see that they are near-Earth objects. They are orbiting quite the same orbit than the Earth. There are small objects because when you start to build large objects, at least their parent bodies, if they are too large, they will differentiate, and then you will lose most of the pristinity of the object, and you will destroy most of the organic content of this object. So these are C-type, B-type asteroids. These are asteroids that are thought from remote observation to be rich in carbon. So Hayabusa 2, you can see there's been mangas that have been made in Japan about this mission, and here you will see the collection. It was not landing, it was a touch and go. And you will see the spacecraft is approaching, you see the shadow of the solar panels, and it just touching. When it touches, there is a projectile, a bullet that is fired, extremely clean bullet that is fired, and then that would eject material. And some of the material will get inside the spacecraft. There has been 2 sample collections in February and July 2019, and the samples were brought back, and they brought roughly 5 grams. So it might sound a very small amount, but it's enough to do science. OSIRIS-REx is the American mission, and you see the sample collection here. So it's impressive to see that these are actual pictures that were taken during the collection. So it's also a touch and go. It went extremely well, and so well that it collected too much material. You can see here a picture 2 days after. You see that there is some parts of the asteroid that is getting out from the sample collection system because it was filled too much, it could not close properly. So, well, they wanted to spin around. It was a way to weigh how much material was collected. And then they did not do that because they were afraid to lose material when they were spinning around the sample collection system around the spacecraft. So here it's our synthetic image. If I can. Okay, the sample is here, and it's brought back to the system that will be sent back to Earth. So this is how it's supposed to work. And this is what happened. These are real pictures. of the capsule, and then click. And next day, they close. Yes. This is not. Everything there are two pictures.
Do they have an estimate of the quantity of material?
Well, they could not do it properly because they wanted to do it, just having the sample here and making the spacecraft do like that. And the inertia moment would help to estimate, but they didn't do it. But they think they have, I've heard, they have something like 100 grams. So it's a huge, huge amount. But it's, well, it still has to go back and be properly recovered. So let's hope for the best. Sample return will be September 24th, 2023. So we know that there is organic matter in meteorites. Here you have two of the most famous meteorites, Murchison. It's like the rock star in the meteorite world because it's been studied. It's one of the first meteorites that has been collected right after its fall, and it fell in Australia in a very dry environment, and so there were very few suspicion of contamination of this meteorite. And it's very important when you detect organic material coming from space to be able to tell whether or not it's contamination, because there's organic material everywhere in your lab. And if you take a rock that stayed for weeks, months, years, or hundreds of years somewhere on the Earth, it would have been contaminated by the Earth environment. And this is the Orgueil meteorite, which is one of the reference of the most pristine material of the solar system. If you want to date the formation of the solar system, you take a piece of such a meteorite and you make your datation on this kind of material. So meteorites are still falling on the Earth, 10 tons a year, roughly. Micrometeorites are much more, orders of magnitude above, but they are smaller and harder to find, 10,000 tons a year. And if you analyze the content of those meteorites, what has been the most impressive, it was found during the 70s, roughly, is that they contain carbon, up to 3% in mass of carbon. So it's roughly one order of magnitude lower than what we estimate in comets, but at least we have it in the laboratory. And we find a large diversity of organic molecules. Among them, amino acids. Amino acids are the building blocks of proteins. Life uses roughly 20 amino acids, but you can imagine many configurations of molecules you would call an amino acid that is not used by life. So that's why we can find more than the 20 we know for life. 92 at the latest estimation, and among them 8 are actual amino acids that are used by life. It doesn't mean that the first organism used those kind of amino acids, but at least you know that amino acids have been imported, and it's still an ongoing process. It's still working, so why not 4 billion years ago? If you look into details about how this carbon is split inside those carbonaceous meteorites, I've not insisted about that, but you won't find carbon in all kinds of meteorites. You have metallic meteorites, you have meteorites that are mostly rocky, so we are interested in what we call carbonaceous chondrite. And these carbons that can make up to 3 to 5% in mass of the body is made of two parts. One part which we call the soluble organic material, which is 10 to 20% of the whole content of carbon of the meteorite, and one part which is called insoluble organic material. But of course, when you say it's soluble, it depends soluble in what. And so to make the inventory, you try to solubilize whatever can be soluble in a series of solvents. It's not necessarily only in water. So just like in comets, you can see that most of the carbon is stored in the form of this insoluble organic matter. But of course, if you are dealing and interested in prebiotic chemistry, you will be interested in the soluble part. And it's in this soluble part that you will find, for instance, amino acids and sugars molecules or nucleobase molecules, those kind of tiny components that build up the proteins or DNA or RNA molecules. You can find them in this soluble fraction. It doesn't tell you how they link together, but those bricks are here. And most of the part is insoluble organic matter. I've already discussed that kind of material yesterday. But you see that it's the same kind of separation between two kind of families in the meteorite than what we find in the comet. But the total amount, the total relative amount is 10 times slower in the meteorites than in comets like 67P. Not only. When people are doing that, they start with hexane, they start with a series of solvents with different properties, and they end with water. And so you analyze each part of each solvent you've used, and then there's still something that you would not solubilize in anything. This is what we call the insoluble organic matter.
Even HF?
HF, it's eating the mineral part. And to extract the insoluble organic matter, you put what remains of your meteorite in HF, fluoric acid, and then an organic material remains. You get rid of the mineral, and you get your insoluble organic matter after HF. But it's not soluble in HF. It's what remains. The mineral is soluble in HF. So the soluble part is dominated by carboxylic acid, and you will find amine, amides, amino acids, alcohols. So the full range of organic material you can imagine. Here it's the same thing, but in the form of a table, so I skip it. An interesting feature too is related to what we called chirality. Chirality is the fact that for some molecules, not all of them, but for some molecules, they have two ways to be organized in a three-dimensional configuration. It's the same thing for your hands. If I take my two hands, they have the same formula, the palm and 5 fingers, but I would never be able to superpose them. It's not working. There are images, each of them in a mirror, but I cannot put them one into the other, unless I break some of my fingers and I change the configuration. I think you don't want to do that, but it's the only way. And this is what is shown here. This is alanine, an amino acid, a simple amino acid, and you would see that they look the same at the first sight, but you would not be able to put them one onto the other. The bold bond here is in front of the screen, and the dashed line here is behind the screen. Life is using only what we call the L configuration of amino acids. And we don't know how and why life decided to use this configuration instead of the other. But it is a fact that in some, not all, some of the carbonaceous chondrite, some, not all, amino acids show a tiny, or not so tiny because it can rise to 15%, for example, for isovalene, excess of the L configuration compared to the D configuration. Not. Only L. So, is it the reason why life chose the L configuration because it was taken from a pool of amino acids that already had a small excess, and then this excess has been selected, amplified? We don't know, but it's an observation. And later, I will show you that we have at least some kind of interpretation of how this kind of excess can be provoked in astrophysical environment. I told you that, yes, the obsession of an astrochemist working on astrophysical material is to be sure you're not detecting something you brought yourself, that is in the instrument, in your laboratory, and you claim, oh, I'm happy, I found amino acids, but it's yours, amino acids. So you can tell because if you were only detecting the 20 amino acids used by life only in the L configuration, then you would have a lot of suspicion it's contamination. You detect much more. You also use isotopic signatures. Here, you have what we call delta D. Delta D is the excess of deuterium in your organic compounds compared to a reference. And the reference is the amount of deuterium in water on Earth. So 1.5 10 to the minus 4, like I told you yesterday. So you use this formula. You take the D over H ratio of your sample minus D over H ratio of your standard water for D over H. Divide by the ratio in your standard. You multiply it by 1,000, and you have your delta D. And you can do the same thing for delta C13 with another kind of reference. And here you can plot your material, and all the terrestrial organic matter lies in this part of the figure. And if you put the material that is analyzed, extracted from the Murchison meteorite, you see that it's not in the same place. If it was a contamination from the Earth, you would have your Murchison material here at the same place of the Earth. And you see that it depends of the family of the organic you are analyzing. So we don't really understand exactly why this excess and difference from Earth is produced. We know that it's clearly not the same than on the Earth. But it's certainly the signature of some kind of complex chemistry that is not the same for each kind of family of organics. I skip this one. Recently, well, I say recently, this paper is 12 years ago. So I start to get old. You would not say it's a recent detection, probably, but it's been really a milestone in the analysis of carbonaceous chondrite. This team, led by Philippe Schmidt-Coplin, they are working in Germany. They use the most advanced technology to analyze carbonaceous chondrite. They use an ultra-high resolution mass spectrometer. I've told you already about mass spectrometry yesterday. So you put everything at the same time, there's no separation before. You put everything in the instrument and it would weight each molecule. The difference between what I explained you yesterday is that the ionization mode for this analysis is extremely soft, which means that you will not break your molecule. You will take away one electron, you will have a charge of the molecule. You need a charge of the molecule to be able to analyze it, but you will not break it. And the conclusion is that there are tens of thousands of different molecular compositions that is present in Murchison meteorite. And how can they do that? They do that using high resolution. Well, I told you yesterday, I think I told you CO2 was 44, which is nonsense. CO2 is 40, C is 12, O is 16, so 2C is 24 plus 16, you reach 40. So this is the mass of CO2. You could also say that N2 is 28, 14 plus 14. And CO, 12 plus 16 is 28. So you can say, okay, I cannot make the difference between N2 and CO with a mass spectrometer because the mass is 28. But it all depends on the resolution, because we learn that carbon is 12, and that's true, carbon is 12, because all the elements' weight is made of based on the fact that we say that 1 mole of carbon is 12. So carbon is 12.00000 all the way. But H is not 1. H is 1.007. And nitrogen is not 14. Nitrogen is 14.003. And oxygen is not 16. Oxygen is 15.99. So if you have the ability to weight precisely these extremely tiny differences, then you will be able to tell the difference between CO and N2, because it won't be 28. It would be 27.9 and so on, or 28 point something. And here, for instance, you see at mass 158, you can have this molecule, C5H10N4O2, and it would weight 158.08 and H0376. And you could tell, if you have the sufficient resolution, you can tell the difference with C10H10N2, because it would be 158.084398. And this is the gross composition. You can imagine, you could play to imagine a different way to associate these atoms to make another molecular structure. And when you put Murchison in this kind of mass spectrometer that is able to go into so much details and a so precise weighting of all your compounds, well, this is what you get. You have peaks everywhere. Each peak, you can tell it's a molecule. And if you zoom around 300, you see that here you have at each nominal mass some kind of forest of peaks. And if you zoom here at 319, well, you see much more. And if you zoom here, you see that between 319.130 and 319.142, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, not molecules, masses. You have the gross formula of each, and you can imagine that behind this gross formula you can have a variety of compounds. 10, 20, 100. Well, it would depend, but you can think about that. Yeah.
How many instruments in the world are capable of this resolution?
This is a FT-ICR. I think they start to spread out, yes, 10, 15 years ago. But now you can use the Orbitrap technology that doesn't go at such a high resolution, but it's enough to do the job. And then Orbitrap based mass spectrometer are now, well, I won't say everywhere, but you can buy an Orbitrap mass spectrometer for well, 100,000 euros, something like that. So it's affordable. Well, it's affordable way to say, but it's the kind of standard big instrument you can have in various laboratories. So it shows you that you can imagine any kind of formula, it's probably there in the Murchison meteorites. It doesn't mean there's life in the Murchison meteorites. It just tells you that, well, naturally, diversity of organic material is occurring. And you don't have to link that to life. And sometimes you might hear, oh, we've discovered this molecule, we've discovered this molecule, it tells us about the origin of life. No, because I will next explain you why it's there, and it's not at all linked to life. But this has been brought to Earth, and this is the kind of play field we are facing for the chemistry. It's complexity, diversity, while life is organization. And that's still a mystery. Yes?
It seems to me that this is such high resolution that if you looked at coal or oil, you might be able to tell which species decayed to produce that oil or coal.
So I'm not a specialist of that, but I've read papers of Schmidt-Copeland team, and they do that kind of analysis on whiskies. Whiskies, champagnes, and they can link the signature to they had a paper about that, to where in Scotland it's come from. So it's and it's used heavily now in biology.
In the police force, to look at the drug.
I don't know. Probably. Well, maybe police force don't have enough money to buy to buy that. And well, and it's well, you need to be extremely well trained and experienced to be able to work with that. It's not I push the button and I got the result. It needs calibration, and it's extremely complicated. And there is also a class of organic compounds that can be extracted from Murchison-like meteorites that are amphiphile. Is it the right way to say it in English? Amphiphile. It means that there is one part of the molecule that is soluble and one part of the molecule that is not soluble. And that spontaneously, the molecule would organize. They don't want anything. They just follow their physical-chemical properties in water. But they would organize themselves to make those kind of vesicles. So it's extremely naive to say, oh, we have membranes. Well, no, membranes are a nightmare. I've already talked about membranes. I've barely understood anything. But these things are simple. But, well, it might be a way to help us to think about how the first compartmentation could have occurred. Whether it is a good idea or not, it's an observation. It's an observation, and it's there. So it can lead to the idea that, okay, in meteorites like that, you have everything. You have soluble material, amphiphilic material, you have reactive molecules, and then you just let evolution and time play the game, and life could arise from that. It's probably not that simple, but it's there. So how it is related to the asteroids, because I told you we don't pick the samples we analyze when we have a meteorite. We are lucky to have a meteorite, but we don't know where it comes from, how representative it is from asteroids. And first result that has been published, I know that there will be a special issue maybe in a few weeks or a few months, but it's already almost ready. But the first results that have been published show that the samples that have been returned from Ryugu with Hayabusa 2 are similar to carbonaceous chondrite of type CI, like Orgueil or Ivuna. And from their analysis, they say that this material has been altered by liquid water, but at relatively mild temperature, 37 plus or minus 10. So this shows that this asteroid, Ryugu, is really linked to the CI class of meteorite we study. And there is, I won't get into too much details, otherwise I will run over time too much, but the content of carbon is the same amount, roughly the same amount that what we found in carbonaceous chondrite. So it was a very good choice, and we now have this relationship between meteorites, carbonaceous meteorites, and a certain class of asteroids. And probably Bennu sample will confirm that, but much more will be published in the next few weeks. I'm telling you about meteorite, but let's not forget that there is much more micrometeorites that are falling on Earth. Some of them are rocky, but some of them are rich in carbon. These are those which are called ultra-carbonaceous Antarctic micrometeorites. They are found in Antarctica. We are lucky in Antarctica to have a not polluted environment, and when you take ice in Antarctica, when you melt it and when you filter it, you would be able to collect tiny microscopic particles. Some of them are from the Earth, but some of them are from an extraterrestrial origin. You can tell it by isotopic signatures that it's not coming from the Earth. And in some of them, you have more than 50% in mass of the micrometeorite that is made of carbon. So that's a huge amount. And that's why we think those meteorites, ultracarbonaceous meteorites, might be linked to comets, because we find the same kind of amount of carbon than in comets. Something is not cometary-like is the nitrogen content of this micrometeorite. They have much more nitrogen than what we found in 67P. So there's still some things we don't understand about those objects. But maybe these are the first particles of comets we have on Earth, and we can analyze in deeper details than we can do with in situ instrumentation. So I've talked about that at length yesterday. Why do we find that? Is it linked, for instance, to what we observe in Interstellar Cloud? This is the Orion Nebula. It's a molecular cloud, and when we observe to that kind of environment, we find a large diversity of compounds. This is observation from the ground. We've never been there, of course. But here, for instance, you see a spectra of what we call a hot core in the interstellar medium. So it's a region where a star is forming. So if you have something that is condensed, it would sublimate, and then you observe in the gaseous phase what has been probably sensitized in the solid phase and is sublimating. So this is in the radio wavelength. So you see a lot of compounds. And if you are looking into the coldest place, then you see another kind of chemistry in the ice phase. You can tell it's in the ice phase because the signature of water here is typical of the way water looks when it's in the form of ice. And you can see methanol, CO2, you can see ions like oxygen, methane, and it's mixed with silicate. So it's a mixture of ice and rocks that is in the molecular cloud. And if you go on this website, it's regularly updated, you have the list of all the compounds that have been detected in the interstellar medium. So the interstellar medium by itself is like a factory of production of organic compounds. Most of the molecules, you cannot read everything, but most of the molecules here are based on carbon. Most of the diversity in the natural, well, life is natural, but in the abiotic chemistry, most of the diversity we observe is based on carbon. How does it form? Well, in the gaseous phase, things might be complicated. But with the help of solid surface, you can explain a lot of the chemistry that we observe. In the diffuse interstellar environment, you can observe tiny particles, silicate particles that are a few tenths of a micron. And when those particles enter a molecular cloud, they get into an environment when the temperature is getting lower and lower, the density is increasing, and then in this environment like that, what you see actually, what you don't see, because you have those particles that are more concentrated than in the surrounding. What you don't see is that kind of silicate nucleus that is surrounded by an icy coating. And on this, at this surface, you have the formation of water, CO, CO2. It can be either formed there, or if it's in the gaseous phase, it would condense around the nucleus. And then, if you have that, and if you simulate that kind of thing in the laboratory, you will see that when you mix an ice mixture made of water, CO, CO2, ammonia, methanol, formaldehyde, for instance, if you simulate that in the laboratory, you will synthesize an organic residue that is made of more complex molecules. Sometimes those molecular clouds would diffuse and not contract until forming a star, and this material would be spread back in the diffuse interstellar medium. In this diffuse interstellar medium, then, this organic coating would get much more radiations. The ice would sublimate because the temperature would rise. In the molecular cloud, the temperature would be around 10 Kelvin. It's extremely cold because, yes, you are the energy of the surrounding stars is hidden by all the surrounding material you have. So inside, it's extremely cold.
Could you be a little bit more specific about how you start out with a dust grain, then you have ice, and then that makes this silicate nucleus or the organic molecules from that combination?
I will later. It's the next step of my explanation. And then it can go back in another molecular cloud, and then you would have ices again condensing and a new layer of organic coating like that. So this is the matter of our natal molecular cloud. And this is what is used to form the solar system. But it's not straightforward. We know that close to the sun, you are in a warm environment, and the solid matter you have is only made of rocks and metals. And when you are further from the sun, then you reach low temperature where you can have, in the solid phase, also ice. Ices. Ice, water ice, of course, is dominating, but there's much more than only water ice there. And all the question is the extent to which this original matter could have been preserved. If you are an icy coated grain from your molecular cloud and you fall here close to the sun, you would reach very high temperature, and all your mineral and organic composition would be changed. Organic would be paralyzed, and you would lose all the organic content of the molecular cloud. But at some distance, you may have keep the original composition. It depends also on the fact that there were some mixing by turbulence in the solar system. So you could fall here, where you are still in the icy phase, but due to the turbulence, you would go close to the sun and be transformed and then ejected further, and then you would find other, you would see more ice condensing onto you, but you would have lost your original composition. But depending on the paper, this mixing by turbulence could extend between 10 to 30 AU, so it's based on model. So maybe at the outer edge of the solar system information, you may have preserved the initial composition of the molecular cloud. But it's still debated whether or not we could have preserved that, because we can observe the interstellar medium. So we know what happened there. We cannot observe what happened 4.5 billion years ago in the protosolar nebula. So this is in this environment that in the rocky planetesimal inner solar system region, you form the planets and asteroids that are the remnants of the formation of the planet. And the outer part of the solar system, you have the region of formation of giant planets and comets. And there's no reason all comets would have the same composition, unless there is a very efficient mixing all the way through the what we call the icy the snow line. Thank you. You read my mind. Between the snow line and beyond Neptune, we don't know. I skip that. So this is what Mayo Greenberg, it was a while ago, thought. This is why he thought that comets could have been made of interstellar medium material. So it's been debated. It's probably not black and white, but that's the idea he was promoting. So these were observations. So now let's try to go in the laboratory and try to understand what is happening. So in my laboratory and many others, we have that kind of device. You have a vacuum chamber inside of which you put a cryostat. You tune the cryostat to 10 Kelvin. 10 Kelvin is hard to get, but 15, it's quite okay. And on your cold plate, you inject a gaseous mixture. And this gaseous mixture is representative of the main compounds that you can detect in the interstellar medium or in the atmosphere of comet. So water, CO, ammonia, methanol, formaldehyde, if you want. And you cool it down. You have an ice layer. And then, if you want to simulate, for instance, the photolysis that can occur due to the UVs of the primitive sun or other suns, other stars in the interstellar medium, or you can connect it to particle accelerators to simulate galactic cosmic rays, well, you can irradiate your sample. And at the end of the day, or sometimes the experiment is during a week, you switch your cryostat off and you let the temperature warming up back to room temperature. If nothing happens, your ice mixture would sublimate at some temperature, because you're under vacuum, so you will not have liquid water, it would directly sublimate. But what happens is that at room temperature, you have some residue that is stuck on your plate. And this residue is made of organic material. This is how it looks. So this picture was taken on a sample plate. It looks like an oily residue, but it's not sublimating. And when you analyze that, well, you see, well, anything you want, mainly. Well, of course, it depends on the starting materials, but you detect a large diversity of compounds that are synthesized. Here you see an example. So this is a spectrum of ice that is irradiated. You see a lot of signature in the in the infrared, but if you put it in a high-resolution mass spectrometer, not FT-ICR like I showed you a few minutes ago, but Orbitrap, which is also extremely powerful, you see the same kind of results. Again, each peak here is a different, not only a different molecule, a different mass, precise mass, and from this mass you can have more molecules that are made of the arrangement of the atoms. And you can see here a zoom at 226.11. You have these assignments for each mass.
Could you give some details on the UV spectra which is being used in the experiment?
So it's hydrogen microwave powered lamp. So it's emitting a Lyman alpha, and depending on the tuning of those lamps, because sometimes you don't use only hydrogen, you make a mixture between hydrogen and helium. Sometimes you also have a bump at 160 nanometers. But the most relevant, what we want to simulate, is a vacuum UV from the stars. So it's a Lyman alpha that is dominating. So somehow it's not a surprise. It's not a big surprise to observe this diversity because we can reproduce it easily in the laboratory. So I know that you're not chemists, but I can't resist to get into some details. So bear with me for a few seconds. But it's not easy to understand because you make a mixture, you irradiate, the only tool you have to try to understand when you're doing the irradiation is infrared, so you don't get into too much details, but people are working a lot, trying to improve, trying to use more techniques. But one of the basics of the starting of what is happening in the laboratory and in the interstellar ices is, for instance, if you have a mixture of water and CO ice, you would hydrogenate your CO to form formaldehyde and methanol. And you have some radicals, the points, the dots that are on the molecules mean that it's a radical, so it's not plus or minus. It's not a charge, formal charge, it's neutral, but you have an electron that is alone. And an electron that is alone on a molecule wants to bond with another electron which is alone. So you can imagine some combination between this radical here, HCO plus CH2OH, and then you get glycolaldehyde or you get ethylene glycol. And if you get from ethylene glycol and glycolaldehyde, you can have glyceraldehyde and glycerol. Glycerol is what is considered as a first molecule that can be placed in the family of sugars. So we know sugar, table sugar, but it's not only it's saccharose, but there is a whole families of sugar. Ribose, desoxyribose are sugars. So we can synthesize sugars with that kind of chemistry in interstellar or precometary ices. Do you want me to get into details? No? But this is what we are dealing with. You know, you probably most of you are astronomers, so you are happy with equations. Chemists, we are happy with that kind of things because this is how we work. And this one is wonderful. I love it because two of my favorite molecules are polyoxymethylene. I told you about it yesterday. There are hints that there is polyoxymethylene in comets. It's not proven, but there are hints. There is polyoxymethylene in comets. And from the chemistry of formaldehyde with a tiny amount of ammonia in water, you can get polyoxymethylene. So it's not complete nonsense to say, hey, maybe there's polyoxymethylene in comets. And my second favorite molecule is hexamethylene tetramine. And this molecule also can be synthesized from formaldehyde, but this time with an excess of ammonia. Yep. And it means that whether or not you find polyoxymethylene, whether or not you find hexamethylene tetramine, if you've done your homework in your laboratory, you can tell the history of the ice. It's detecting this or this molecule is not okay, we've detected this molecule. It means something about the processes that led to this formation. Yes?
Yeah, Hervé, you've shown us hundreds and hundreds of molecules, and it's making me ask the question, what can't you produce? Not what can you produce. And the reason I'm asking that is that's an important question for the origin of life, because when I talk to synthetic chemists who are trying to make life, sometimes they say, oh, this is hard to make, this is hard to make. But you seem to be able to make everything here, so what can't you make? I don't understand this too. You're making everything, and they're having problems making life, so where...
We don't produce DNA or RNA nucleotides like this. We don't link the thing. In some experiments, people say they have some dipeptides, but well, most of the time they need liquid water before that. What we don't produce for sure is organization. It's a mess.
How about polymerization, dipeptides, for example, or oligopeptides?
In some experiments, we do. But I'm talking about amino acids right now. So it's kind of iconic. Amino acids, if you are able to synthesize it, it makes you into the news. And you have amino acids that are synthesized. But
do you make dipeptides or tripeptides?
Not easily. Not easily. I'll come back to that later. But most of the time, to analyze these amino acids, you take your residue, you put it into liquid water, and you make it into 6 mol per liter HCl at high temperature for, well, it depends on the procedure, for hours. So you are adding some chemistry in the liquid phase and in acidic condition. And then, yes, you get a lot more than what you get just with the ice irradiation. So it's still an open debate. People say, okay, but you put the original material in water on the primitive Earth, and what happens in the primitive ocean or warm little ponds, if you want, is the same thing that we reproduce with the acid hydrolysis. Well, being a chemist, I'm not that sure that it's exactly the same chemistry. And actually, people doing that kind of things now are trying to brew their organic residue in very mild condition to try to analyze exactly what is produced in the ice and not what is the result between what is produced in the ice plus the chemistry in liquid water. But it's not straightforward. Glycine, amino acid, the king of the zoo from the Rosetta diversity. Well, for me it was not a surprise because we know since a while. I won't tell you that 2010 paper is a recent one this time. But here, you take CO2, methylamine, CH3, NH2, so CO2 is detected in the atmosphere of comet, methylamine 2. You freeze those two guys together. You just warm first those two molecules and they will react. So it will be just like some kind of acid-basic reaction. And you form a salt, methylamine carbamate, methyl carbamate. And then you put some UVs and you get glycinate, which is a salt of glycine. So in 2 steps, you get glycine from those two very simple and abundant molecules. So we actually not seeing glycine in a comet would be surprising. And those people working in Marseille, in France, they tried to make other amino acids, and they did not succeed. So for me, it makes sense that if you don't have a liquid phase alteration, you may not find anything more complex than glycine in the term of amino acids. Chirality, and I will finish on that. With the same kind of experiment, so you freeze a mixture of ices and you photolyze it, but you don't photolyze it with the random UV lamp you have in your laboratory. You have to go in a synchrotron facility, and then you will produce a circularized polarized light, which means that your photons won't have any random directions when they would be emitted by the source. They would have a specific orientation. And what has been found in this paper is when you start irradiating ice analog, if you do it in your laboratory, and if you find amino acids after the hydrolysis and all the steps I've just mentioned, you would find what we call a racemic mixture. 50% of one configuration, 50% of the other configuration. If you do the photolysis with light that is polarized in a certain way, in the left way or in the right way, then you would increase the formation of the L or the D configuration of the molecules. And this is what is shown here. If you use right polarized light, you would get an enantiometric excess of L configuration, and if you use left circular polarized light, you would get an excess of the right configuration. It's the opposite way. So what is still debated is whether it's formed more in a preferential way this way, or if you form a racemic and the polarized light would destroy more preferentially one form or the other. It's still unclear. But it makes a consistent astrophysical scenario, because we know we don't observe polarized UV light, but I think it's in the Orion nebula, we observe infrared light which is polarized, which means that there is a UV counterpart. So this kind of polarization naturally occurred in the interstellar medium, and this might be why we find this excess in meteorite. Note that I use might, may every time. But it makes sense. We cannot go beyond that, but it makes sense. Okay. UM material, if you put your residue and you keep it irradiated, then you will get less and less and less soluble material. And after a lot of energy, So you start with the simple ice mixture, you get a complexity of fancy, nice, reactive molecules, but you keep on irradiating, keep on irradiating, keep on irradiating. You will have a residue that has some properties that are similar to the insoluble organic matter that is found in Murchison here, or Tegish Lake, which is another meteorite. So that could be the story of the insoluble organic matter we find in meteorite and maybe in comet. But there are other ideas. People say that there can be also some organic chemistry that can occur near the star at warm temperature using gas phase chemistry that would interact with solid, dusty particles that could catalyze synthesis. And it's efficient. In the laboratory, we see it can be efficient. So I'm working on the ice chemistry. So I'm talking more about ice chemistry. But I cannot not mention that there could be other way. And, well, we try to decipher this chemistry and try to understand whether or not it's more interstellar icy heritage or a protosolar nebula chemistry that we find in these meteorites. Okay, so I'm done. Some words of conclusion. So yes, we need laboratory experiments. We need to go to the lab. You cannot just pretend to understand everything just by remote observation. It's extremely important to do laboratory experiments. And it's a wonderful playfield for chemists, but I won't go very far if I wouldn't have physicist colleagues in my laboratory. We are really working together because we would not be able to progress without being interdisciplinary. And yes, maybe I can mention that. Life is more about organization of this complexity. So it's not finding new molecules that necessarily will help you to understand the origin of life. Now we know that we can have any kind of organic compounds we want. And the main job remains in the hand of prebiotic chemists who want to be able to synthesize the first proteins, the first nucleotides, and this is a real challenge because you don't want to do it in a tube in the laboratory. You want to do it in something that is relevant of the primitive Earth. And in the primitive Earth, you had this mess I just mentioned. And sometimes having a lot of molecules is not helping because reactions are in competition. So what we do with two molecules and you have wonderful synthesizes might be poisoned because you would have a third or a fourth compound that would lead the chemistry to a completely different direction. Thank you.
So thank you, Hervé, for the very nice talk. So questions?
Very nice talk. You talk about chemistry that's facilitated by ultraviolet light, but what about cosmic rays?
Cosmic rays, so it's done. When I was a postdoc, long time ago, I was actually I was at Goddard, and we had a Van de Graaff accelerator, so we could play with high energy particles. So mostly doesn't change much of the chemistry. The only thing that is a real difference is that if you have N2, nitrogen, which is frozen, with UV, it wouldn't change. It's not photolyzed at Lyman alpha. So, but with radiations, with high energetic particles, you would be able to break N2 and then get your nitrogen more easily into the game of the chemistry that is occurring. Otherwise, it's not that different. It goes deeper into the ice. If the UVs are absorbed within a few a fraction of micrometer at this wavelength in the vacuum UV. If you have particles that are more energetic, you would get deeper into the ice, and so you will produce much more of the residue that I've talked about. And yes, and the thing is that probably it's a combination of the two kind of photons, cosmic rays are together in space. And in the laboratory, usually we study either UVs or cosmic rays simulators separately.
Thank you.
So another question?
Hi, Hervé. Thank you for the talk. I was wondering, are those carbonaceous asteroids more difficult to detect? Because since they have a larger concentration of carbon, I don't know if I can assume that they would have a lower albedo. I don't know if that contributes in the detection.
Yes, they have a lower albedo, and we think that's because of the carbon. Although it's, well, you know, when you start to discuss something that seems obvious with the people who are really working on the question, you open a door and you have to follow a never-ending thread of people that are disputing and not agreeing. But that's the way science is proceeding. But no, I would not say it's more difficult. It's I've never heard people saying that. I'm not working on actual observation of asteroids, so I'm not confronted directly to this question. But no, it's what is impressive when you look at the classification of asteroids from outside, not working in that. It's that they are mostly have a very limited amount of observation, and they look at the spectra and they look at the slope of the spectra, and they say, okay, it's bluer, it's redder, because the slope in the visible would have different shapes, and then they assigned a shape of spectrum to a family, but based on criteria that why, when you look at it, you say, why this one is not in this family and this one in this other family? It's very tiny differences that are that are used to put asteroids in the various families. But actually it worked, because for Hayabusa they aimed at a rocky asteroid and they brought rocky material, and from Ryugu, let's hope it's the same for Bennu, they aimed at a carbonaceous asteroid, and yes, they brought something like, looks like a carbonaceous chondrite. So it's successful.
Okay, thank you.
Okay, thank you. Another question?
Yeah, Hervé, I'm still concerned about how you start out with a dust grain, and then you got a bunch of ice on it, and then you added some other stuff. And could you talk about that, how that other stuff got there? Is it just UV photons hitting the different types of ices, then the ices combine with each other, and that produces the mantle around the dust grain, or what?
So two things. The one thing is that you, in the molecular clouds, you can have already molecules, and then they freeze at the surface of the dust particles.
Yes.
And the other thing is that you can have synthesizes at the surface. For instance, you have
But once you get the ice there, that kind of undoes the effectiveness of the surface to do that, right?
I don't know if usually people in the lab working on surface are working on mineral surface. Whether or not there could be some surface chemistry at the surface of the ice is not something I would exclude necessarily.
Okay.
And once you are in the ice, for instance, here you start with just water and CO.
Yeah.
This process occurs in ice.
Do you need any
But you need photons. Yes, you need
photons.
photons. Yes, you would. It would not happen without energy. Photons or particles. And then you start with that.
But wait, if you're producing it from photons, why would it then be on the outside of the dust grain? You drew a picture of the dust grain in the middle and then the mantle around it, but you're just describing surface chemistry here.
Not necessarily, because this can, as deep as the photons can go.
But also at the surface.
But also at the surface, yes.
But you drew this orange thing uniquely around that dust grain.
Yeah, because it's my skills in
So that orange could have been anywhere. Is that what you're saying?
Well, no, because the idea. Let me check my animation. Yes, the idea is that when you do your chemistry all around that, and then yes, this mantle usually is sensitized when the ice is warming, because you have, if it's cold.
But it's not warming from the center.
No.
The source of heat is from the outside.
I agree discussing with you that this.
So why don't you have a mantle crust? I mean, an organic crust rather than an organic mantle.
No, because what I wanted to say is that once the ice is sublimating, what is remaining is the mantle around the silicate nucleus.
Also,
that was my point.
So if I've understood, when you're producing this orange stuff, it's everywhere, but then the ice preferentially sublimates, and then that leaves the mantle.
Yes.
Would it be porous?
I don't know. What we have in the laboratory, it's a picture. Here it's like an oil. It's still liquid there, but it depends on the dose. It's like when you, the example I like a lot is when you want to prepare caramel. You put saccharose in your pan, and then you heat it. And then it would condense, and then at some point you will have your caramel. So if you want it extremely liquid, you stop the cooking quickly. If you want it more hard, you wait a little bit more. And if you mess up with your caramel preparation, you have a dark, sticky residue, and you have to put your pan in the trash. And it's a kind of illustration of what is occurring here. You get more and more complex materials that will be less and less soluble and more charcoal-like in the end, and insoluble.
The reason I keep on talking about this is because we would like to know what the ice or the water to rock ratio is in Jupiter and Saturn, Uranus and Neptune, and ask the question in general, what is the water or ice to rock ratio in general in the universe? But in general, there's more ice and water than there is rock. We know that from the cosmic abundances. But when I ask people about what's the water to rock ratio, they typically say sometimes 1 to 1. Or in a comet, you've already lost a lot of the stuff, and so you have more, more rock than water. And so it's an important variable.
And I think that what people might miss in the picture is refractory organics, because it's not necessarily half water, half rock. It would be interesting to consider half water, half organic, not half, 1/3 of water, 1/3 of organic, and 1/3 of rock.
So the picture you're telling us is you take these various ices, you irradiate them with photons, and that produces this organic material of various kinds, both soluble and insoluble. Is that right?
Yeah. And it's there. It's what we find in the comet. But we were discussing it, I think, in the car. For Rosetta, people from different instruments don't agree about the dust over ice ratio in the nucleus. When I make my calculation, when I show you the pie chart about the composition of the nucleus, I take a ratio of 3. So I don't make too many enemies using 3, because for some people it's the upper limit, and for some other it's the lower limit. But it's
3 parts rock to 1 part ice? Or the
dust to ice, yes.
Okay.
Dust to ice is 3. It's a dry comet.
But that's not the same. It's the inverse of a grain in a molecular cloud, where you have more ice than dust on a grain. Isn't that right?
I don't know.
Just a comment concerning your last sentence, when you wrote that life is more an organization of complexity.
Yes.
So the question is how to get this organization. It's not money and power. Yeah, definitely. Okay, so let's thank Hervé again.